All right, so if you've been working with sampling, you know cluster sampling is a really powerful tool. But, in the real world, things get messy. Those neat textbook examples, they kind of fall apart because clusters are almost never the same size. So what do you do then? Well, in this explainer, we're going to dive right into that problem. How do you get accurate estimates when your clusters are all different shapes and sizes? So here's our game plan. First, we'll really get a handle on the challenge itself. Why do unequal sizes throw a wrench in the works? Then we're going to compare two ways to deal with it, the unbiased estimator and something called the ratio estimator. After that, we'll do a deep dive into that ratio estimator, and then the best part, we'll walk through a whole case study, calculating our final estimate from start to finish.
Okay, let's kick things off by understanding exactly why these unequal cluster sizes can be such a huge headache for us. It really all comes down to one thing: variance.
Now, just to make sure we're all on the same page, let's talk terms for a second. When I say PSU, or primary sampling unit, I'm just talking about the cluster itself, the groups we're sampling first. In the example we'll look at later, these are going to be classrooms. And in one-stage cluster sampling, it's simple. Once we pick a PSU, we measure every single person or thing inside it.
So here it is. This is the heart of the problem. The total value we're interested in for a cluster, which we call T sub I, is very often directly tied to the size of that cluster, M sub I. Just imagine you're sampling postal routes to estimate unemployment. A huge route with 500 houses is almost guaranteed to have a higher total number of unemployed people than a tiny route with just 50 houses, right? This direct link creates this massive variation between the cluster totals, and that, in turn, just blows up the variance of our overall estimate.
So how does this actually wreck our standard approach? Well, if we try to use the normal, unbiased estimator for the total, its precision, its reliability, hangs entirely on that S-squared's t-term. That's the variance of our cluster totals. And when those totals are all over the map because the cluster sizes are wildly different, that value, just like the note says, it just explodes. It sends our standard error through the roof, and we're left with a really imprecise, kind of useless estimate. Okay, so if the standard way of doing things has this major flaw, what do? How do we get around it? Well, when we're trying to estimate the population mean, it turns out we have two main paths we can go down. So on one hand, you've got the classic, by-the-book, unbiased estimator. You take your estimated total and divide by M naught, which is the total number of elements in the entire population. Sounds great in theory, but it smacks into a huge real-world wall. We almost never actually know what M naught is. And this is where the ratio estimator comes in with this really elegant fix. Instead of needing the true total population size, it just estimates it from the sample you already have. It's a brilliant little statistical hack that gets us around a massive practical problem.
And this table right here shows exactly why that hack works so well. Look at the variance for the unbiased estimator. It's driven by that super volatile S-squared T term. But now look at the ratio estimator. Its variance is driven by something totally different, S-squared E, the variance of the residuals. Now, what's a residual? Think of it like the surprise factor for each cluster. It's the difference between its actual total and what we'd predict its total would be, just based on its size. When size and total are strongly connected, those surprises are really small, which makes our overall variance shrink a lot.
Now, to actually use this thing and build confidence intervals, we've got to get comfortable with its standard error formula. I know it looks complicated, but trust me, each little piece tells an important part of the story. Okay, I know this looks like a beast, but let's tame it piece by piece. First up, you've got that 1 minus n over n term. That's just our old friend, the finite population correction. It gives us a little precision boost for sampling without replacement. The real action is inside that square root. We divide by n, our sample size, which makes total sense. More samples, less error. But we're also dividing by m bar squared. Why? That basically scales everything, putting the variance on a level playing field relative to the average size of the clusters we sampled. And that last part, the summation, that's the engine. It's summing up those squared surprises or residuals we were just talking about.
So what's the big takeaway from that complicated formula? It really boils down to this. The precision of our estimate doesn't depend on how wild the cluster totals are. Instead, it depends on how consistent the cluster means are. If every single classroom, whether it's big or small, has an average test score that's hovering right around, say, 60, then our variance is going to be tiny and our estimate will be super precise.
Theory is one thing, but the absolute best way to really get this stuff is to see it in action. So let's roll up our sleeves and get our hands dirty with a real example. Okay, here's the setup.
We're looking at a city with a total population of 187 high school algebra classes. Our goal is to estimate the average test score for every single student across all those classes. Now, testing everyone is way too expensive, so instead, we take a simple random sample of just 12 classes. Then, for those 12 classes, we test every single student inside them. And the key detail here is that the classes have different numbers of students. It is the perfect setup for our ratio estimator.
And now for the main event. Let's take the data from this study and walk through the whole calculation step by step to get our final estimate and a solid confidence interval. All right, here's the raw data from our 12 sampled classes. The first thing you should notice is that M sub chi column, the class size. See? We've got classes as small as 20 students and others as big as 26. This is exactly the unequal size problem we've been talking about. Now, for each class, we have its average score and its total score. And that final column? That's that squared surprise term we talked about. And we're going to need that in a minute. For now, let's just focus on the totals at the bottom. 299 students tested in total, giving us a combined score of 18,708. So we're going to follow a really clear three-step process here. First, we'll calculate our best guess for the mean. Second, we'll calculate the standard error to figure out how uncertain we are. And third, we'll use those two numbers to build our 95% confidence interval. Simple as that. So step one is beautifully simple. Our best estimate for the overall average score is just the total of all the scores from our sample divided by the total number of all the students in our sample. So we just take 18,708 and divide it by 299. And that little bit of math gives us our point estimate, 62.57. So if someone stopped you on the street and said, "Quick, what's your single best guess for the average algebra score in this entire city?" This is your number. But of course, as statisticians, we know a single number is only half the story. The real question is, how much should we trust it? Okay, on to step two, calculating the standard error. We're going right back to that big formula, but now we get to plug in our real numbers. We start with the finite population correction, since we sampled 12 out of 187 total classes. Then we scale it by our sample size of 12 and the average class size squared. And finally, the engine of the whole thing. We plug in that 194,827, our total sum of squared errors, and we divide that by n-1, which is 11. And after you run all those numbers, you get a standard error of 1.49. So what does that really mean? Well, you can think of it as the typical wobble in our estimate. If we were to do this whole sampling experiment over and over again, our sample mean would typically be about 1.49 points away from the true citywide average. It's our measure of precision. And that brings us to our final step, building our 95% confidence interval. We take our point estimate, 62.57, and we add and subtract a margin of error. That margin is just our standard error, 1.49, multiplied by a critical value from a t-distribution. Since we have 12 clusters, we use n-1 or 11 degrees of freedom, which gives us a critical value of 2.20. And that gives us our final range, from about 59.3 to 65.9. We are 95% confident that the true average test score for all students in the entire city is somewhere in that interval. And just to bring this all home, check this out. This is the output from running the exact same analysis in R using the survey package, which is really the gold standard for this kind of work. And would you look at that? The results for the mean and the standard error are identical to what we just calculated by hand. This proves we did it right, and it shows you exactly how this is done in the real world. So what's the big takeaway here? What's the bottom line? It's that when you're out in the real world, dealing with clusters that are all different sizes, and there's a connection between a cluster's size and its total, you can't just ignore it. The ratio estimator correctly uses that relationship to give you a much more stable, much more efficient, and ultimately, a much more useful estimate of the population mean.